Let us learn what is the circulatory system, what it does, how it functions, and why it is vital for life to exist. The cardiovascular system functions complementarily with other organ systems to make up a living being. It delivers oxygen, nutrients, hormones, and other substances to and picks up waste, such as carbon dioxide, from cells near sites of exchange via blood. Waste buildup in tissues. Body organs fail to function properly, and then once oxygen is depleted, they will die. Organs of the cardiovascular system are the heart and blood vessels. Approximately the size of a person's fist. It is located in the medial section of the thoracic cavity, flanked laterally. The heart is enclosed by the pericardium, which is made up of 3 layers: the fibrous pericardium, the parietal pericardium, and visceral pericardium, or epicardium. The fibrous pericardium helps protect the heart and anchor it to the diaphragm, sternum, and etc. Deep within these fibrous layers are the serous pericardial membranes, the parietal pericardium, and the epicardium, which produce lubricating serous fluid to be collected in the pericardial cavity to protect the pericardial layer from friction as the heart beats. The heart walls are composed of 3 layers: epicardium, visceral pericardium, myocardium, and endocardium. The epicardium is the outermost layer. The myocardium, which is also internally structured by the skeleton of the heart, are made of intercalated discs containing both desmosomes, which hold things together, and Gauss junctions, which allow ions to flow from cell to cell. It is the layer that actually contracts. Lastly, the innermost endocardium, which helps blood flow smoothly through the heart, is a thin, glistening sheet of endothelium that lines the heart chamber. Speaking of the heart chambers, the heart has 4 hollow cavities or chambers, 2 atria, receiving chambers, divided by the interlateral septum, and 2 ventricles or discharging chambers, divided by the ventricular septum. The heart and its chambers participate in the pulmonary and systemic circuits. In the pulmonary circuit, the blood is sent out to the lungs through the pulmonary arteries, where it picks up oxygen, unloads carbon dioxide, and goes back to the heart through the pulmonary veins. This circuit starts from the right ventricle to the lungs and back to the left atrium. Moreover, oxygen-rich blood returned to the left atrium is pumped by the left ventricle down to the systemic arteries, essentially to supply all body tissues, and then goes back to the right atrium via the systemic veins, which finally empty their cargo into either the superior or inferior vena cava. This circuit, from the left ventricle through the body tissues and back to the right atrium, is called the systemic circulation. While the heart regulates the transport and distribution of the blood, it is important to prevent backflow of blood in the heart. And we have 4 valves to do the job: the AV valves, left AV valve, mitral, bicuspid, and right AV valve, tricuspid valve. Prevent backflow into the atria when the ventricles are contracting. And the semilunar valves, or pulmonary semilunar valve, and aortic semilunar valve prevent backflow into the ventricles when the heart is relaxing. The valves open and close in response to pressure changes in the heart. Moreover, let us take a look at the cardiac circulation. The functional blood supplies that oxygenates and nourishes the myocardium is provided by the right and left coronary arteries. The coronary arteries and their major branches are compressed when the ventricles are contracting and filled when the heart is relaxed. The myocardium is drained by cardiac veins, which empty into a large vessel on the coronary sinus, which then empties into the right atrium. Now let us go over the physiology of the heart: intrinsic conduction system, cardiac cycle, and heart sounds. In one day, the heart pushes the body supplies of 6 quarts or so of blood through the blood vessels over 1,000 times. Cardiac muscle is able to initiate its own contraction in a regular and continuous way, but its rate is influenced by both intrinsic and extrinsic. The intrinsic conduction system increases the rate of the heart contraction and ensures that it beats as a unit. Extrinsic factors include neural and hormonal stimuli. VSA node has the highest rate of depolarization in the whole system. It starts each heartbeat and sets the pace for the whole heart, thus often called the pacemaker. Cardiac cycle and heart sounds. In a healthy heart, the atria contract simultaneously. Then, as they start to relax, the ventricles began to contract. Systole and diastole means heart contraction and relaxation, respectively. The term cardiac cycle refers to the events of one complete heartbeat during which both atria and ventricles contract and then relax. Cardiac output. The pumping action of the healthy heart maintains a balance between cardiac output and venous return. Cardiac output, the amount of blood pumped out by each ventricle in 1 minute, is the product of heart rate, HR, times stroke volume, SV. SV is the amount of blood ejected by a ventricle with each beat. Factors modifying basic heart rate. Neural controls the autonomic nervous system. Hormones and ions. Examples are epinephrine and thyroxine, calcium, sodium, and potassium ions. They modify heart activity. Physical factors. Examples are age, gender, exercise, and body temperature. The heart is a double pump and each side can fail independently. If the heart on the left part fails, pulmonary congestion occurs. The right side of the heart continues to propel blood to the lungs, but the left side is non-functional, so the needs of the tissues are not met. So CHF occurs and blood backs up in the lungs, causing pulmonary edema. If the right side of the heart fails, peripheral congestion occurs as blood backs up in the systemic blood vessels. The blood circulates inside the blood vessels, which form a closed transport system called the vascular system. The arteries, which transport blood away from the heart, and veins, which carry blood back to the heart, are conducting vessels. Only capillaries, which is only a single layer thick, play the role of actual exchanges with tissue cells. The walls of arteries are usually much thicker than those of veins. This structural differences is related to a difference in function of these two types of vessels. Arteries must be able to expand as blood is forced into them and then recoil passively as the blood flows off into the circulation during diastole. Veins have thinner walls because the pressure in them tends to be always low, yet they are modified to ensure that the amount of venous return equals to the amount of the cardiac output to help return blood to the heart. Moreover, larger veins also have valves that prevent backflow of blood. As the large arteries branch, blood moves into successively smaller arteries and then into the arterioles, which feed the capillary beds in the tissues. Capillary beds are drained by venules, empty into veins, and empty into the great veins, vena cava. Capillary beds have two types of vessels, a vascular shunt and true capillaries. Blood flow into true capillaries is controlled by precapillary sphincters. Exchanges with tissue occur across the walls of the true capillaries. When the precapillary sphincters are closed, blood flows directly through the vascular shunt. The flow of blood from an arteriole to a venule through a capillary bed is called microcirculation. Microscopic anatomy of blood vessels, tonics. Except for capillaries, blood vessels are composed of three tonics: the tonica intima, which forms a friction-reducing lining for the vessel; tonica media, the bulky middle layer of smooth muscles and elastic tissue; and tonica externa, the protective outermost connective tissue layer. Now let us dive into a gross anatomy of blood vessels. The aorta is the largest artery of the body, and it is a truly splendid vessel. In adults, the aorta is about the size of a garden hose, with an internal diameter about equal to the diameter of the thumb, where it leaves the left ventricle of the heart. It only decreases slightly in diameter as it runs to its terminus. The different parts of the aorta are named for their location or their shape. Now let us dive into the parts of the aorta. The ascending aorta, it is upward part of the arc and is the section closest to the heart. And then the aortic arc, it is a section of the aorta between the ascending and descending aorta. Let us move on to the branches of the ascending aorta. The only branches of the ascending aorta are the right coronary artery and left coronary artery, which serves the heart. Next is the arterial branches of the aortic arch. The brachiocephalic trunk. It is the first branch of the aortic arch. It splits into the R common carotid artery that branches into the R internal and R external carotid arteries and the R subclavian. The left common carotid artery, it divides forming the left internal carotid that serves the brain and the left external carotid that serves the skin and muscles of the head and neck. And then, the left subclavian artery, it is the third branch of the aortic arch. It gives off an important branch, the vertebral artery, which serves part of the brain. Additional info to ponder. In the axilla, the subclavian artery becomes the axillary artery and then continues into the arm as the brachial artery and supplies the arm. At the elbow, the brachial artery splits to form the radial artery and ulnar artery that serves the forearm. Next is the arterial branches of the thoracic aorta. The intercostal arteries, it has 10 pairs and supplies the muscles of the thorax wall. The bronchial artery that supplies the lungs, the esophageal artery that supplies the esophagus, and the phrenic artery that supplies the diaphragm. The last is the arterial branches of abdominal aorta. The celiac trunk, a single vessel that has 3 branches, namely the left gastric artery, which supplies the stomach, the splenic artery, which supplies the spleen, and the common hepatic artery, which supplies the liver. The impaired superior mesenteric artery that supplies most of the small intestine and the first half of the large intestine or the colon. The right and left renal arteries that serves the kidneys. The right and left gonadal arteries that supplies the gonads. They are called the ovarian arteries in the females that serve the ovaries, and the testicular arteries in males that serves the testes. The lumbar arteries that are several pairs of arteries serving the heavy muscle of the abdomen and trunk walls. The inferior mesenteric artery is a small, unpaired artery supplying the second half of the large intestine. And the last is the right-left common iliac arteries are the final branches of the abdominal aorta. Each divides into an internal iliac artery, which supplies the pelvic organs such as the bladder, rectum, and so on. Here is a provided picture for a better visualization of the arteries in the body. Now let's talk about major veins and systemic circulation. The arteries are located in well-protected body areas. There are veins that are superficial and some are easily seen and palpated on the body surface. The veins draining the head and arms empty into the superior vena cava, and those draining the lower body empty into the inferior vena cava. The veins draining into the superior vena cava are listed in a distal to proximal direction and has the same direction with the blood that flows to the superior vena cava. Here are the veins draining into the superior vena cava. First is the radial vein and the ulnar vein are deep veins draining the forearm. They unite to form the deep brachial vein, which drains the arm and empties into the axillary vein in the axillary region. The cephalic vein provides for the superficial drainage of the lateral aspect of the arm and empties into the axillary vein. The basilic vein is the superficial vein that drains the medial aspect of the arm and empties into the brachial vein proximally. The subclavian vein receives venous blood from the arm through the axillary vein and from the skin and muscles of the head through the external jugular vein. The vertebral vein which drains the posterior part of the head, the internal jugular vein that drains the dural sinuses of the brain. The brachiocephalic veins, right and left, are large veins that receive venous drainage from the subclavian, vertebral, and internal jugular veins on their respective sides. And lastly, the azygos vein, a single vein that drains the thorax and enters the superior vena cava just before it joins the heart. And for the veins draining into the inferior vena cava, the first vein is the anterior tibial vein and posterior tibial vein, and the fibrillar vein drain the leg. The great saphenous vein are the longest veins in the body. They receive the superficial drainage of the leg. The right and left common iliac vein is formed by the union of the external iliac vein and the internal iliac vein on its own side. It also drains pelvis. The right gonadal vein drains the right ovary in the females and the right testicle of the males, and the left gonadal vein empties into the left renal vein superiorly. The right and left renal veins drain the kidneys. The hepatic portal vein, a single vein that drains the digestive tract organs and carries this blood through the liver before it enters the systemic circulation. And lastly, the right and left hepatic veins, which drains the liver veins. And now, let us move on to the arterial supply of the brain and the circle of Willis. A lack of blood for even a few minutes causes a delicate brain cells to die. A continuous blood supply to the brain is crucial. The brain is supplied by two pairs of arteries, the internal carotid arteries and the vertebral arteries. The internal carotid arteries is a branch of the common carotid arteries that run through the neck and enter the skull through the temporal bone. The paired vertebral arteries pass upward from the subclavian arteries at the base of the neck. Within the skull, the vertebral arteries join to form a single basilar artery. Basilar artery serves the brainstem and cerebellum as it travels upward. And at the base of the cerebrum, the basilar artery divides to form the posterior cerebral arteries, which supplies the posterior part of the cerebrum. The anterior and posterior blood supplies of the brain are united by small communicating arterial branches. The result is a complete circle and connecting blood vessels called the cerebral arterial circle or the circle of Willis. The circle of Willis protects the brain by providing more than one route for blood to reach brain tissue in case of a clot or impaired blood flow anywhere in the system. And now, let us move on to the hepatic portal circulation. The veins of the hepatic portal circulation drain the digestive organs, spleen, and pancreas and deliver this blood to the liver through the hepatic portal vein. The major vessels composing the hepatic portal circulation include the inferior and superior mesenteric veins and spleen, the splenic vein, and the left gastric vein. The inferior mesenteric vein drains the terminal part of the large intestine, drains into the splenic vein. The splenic vein also drains the spleen, pancreas, and the left side of the stomach. The splenic vein and superior mesenteric vein drains the small intestine and the first part of the colon and joins to form the hepatic portal vein. The left gastric vein drains the right side of the stomach and drains directly into the hepatic portal vein. Look at the picture. Another topic that we will be tackling is the physiology of circulation. A fairly good indication of the efficiency of a person's circulatory system can be obtained by taking arterial pulse and blood pressure measurements. These measurements is referred as vital signs in clinical settings. The alternating expansion and recoil of an artery that occurs with each beat of the left ventricle creates a pressure wave and termed as pulse. Pulse travels through the entire arterial system. The pulse averages 70 to 76 beats per minute in a healthy resting person, and it is influenced by activity, postural changes, and emotion. These same points are compressed to stop blood flow into distal tissues during significant blood loss or hemorrhage, and they are called pressure points. The chemicals. There are several and well-known effects of chemicals like drugs and blood pressure. Just like the epinephrine, it can increase both the heart rate and blood pressure. Lastly, the diet. A diet that is low in salt, saturated fats, and cholesterol can help in preventing hypertension. This is all for this video.